Happy Thanksgiving, and here we are with center of mass. So simply put, center of mass is the average position of mass in an object or in a system of objects. So in considering center of mass for a single object, we are expanding our view from the particle model to consider the size and shape of objects. We will also consider center of mass for collections of particles. And in terms of momentum and conservation of momentum for now, that's where our focus will be. When we start considering rotation and torque and angular changes in motion, then we'll consider center of mass for continuous objects. So the idea is the average position of mass. So places in the object with more mass or more density, you could say, have the center of mass closer to them than places in an object where the density of mass is less. Here's an example of how we want to think about the center of mass. In this series of pictures, the diver's motion is pure translation in part A, and in part B, it's translation plus rotation. So translation means movement in either one or two dimensions, like linear movement, and then rotation, of course, means movement around a fixed point. So in both cases, there is one point that takes the same path, and it takes the same path that a particle would take if it were subjected to the same forces as the diver. And that one point is the center of mass. So the average position of mass acts like the place where we could put a particle in exchange for that extended object and follow what we have been doing with the particle model. The general motion of an object can be considered as the sum of its translational motion, as the sum of the translational motion of the center of mass plus rotational, vibrational, and other forms of motion about that center of mass. So this idea is a little bit, again, moving beyond where we are right now, but moving into the rotational dynamics portion of the course. But we will consider rotation and translation and how those two things interact with an object. So how do you find the center of mass? So now we go back to the particle model. So for two particles, we take the average, the mass weighted average of the particle's position. So we look along the x component. So we look along, I don't want laser pointer, I want pen. We look along the x direction, right? I look from left to right. Well, that's totally not a straight line, but I look from left to right and I see where each particle is. So I see object A with mass A is at its position x subscript A. Object B with its mass subscript B is at position x subscript B. And so I say mass A times its position in the x direction plus mass B times its position in the x direction. And then because it's mass weighted, I divide that by the total mass. So MA plus MB can be substituted with capital M, meaning the system mass. We'll do some examples of calculation like this. It's not terribly complicated, but getting a handle on this idea of average position of mass is complicated. So center of mass is the average position of mass. Center of gravity is the same as the center of mass as long as we're in a system where the acceleration due to gravity is constant. So we're working within the flat Earth approximation where acceleration due to gravity is constant as we move up and down in altitude. And so we're within that conceptual structure. The center of gravity is the point where the gravitational force can be considered to act. So again, we're kind of translating between continuous objects and sort of looking at an object that has size and shape and dimension versus the particle model description of that object. So center of gravity is the point where the gravitational force can be considered to act. It's the same as the center of mass as long as gravitational force does not vary among different parts of the object. So as long as the object's relatively small and we're in the flat Earth approximation, and we will only consider cases such as this in this course. The center of gravity can be found experimentally, so you don't have to take the average position of mass, which for continuous objects becomes an exercise in integrals and is beyond the scope of this course. You can find it experimentally By suspending an object from different points, the center of mass does not need to be within the actual object. The center of mass or center of gravity is the place where the line continuing below where you suspend the object. For some reason, I cannot draw a straight line with this thing, but the place where those two lines crisscross. And we'll look at, again, some examples of this. So we're looking at suspending this object from the white dot and the straight line below that, and then turning it and suspending it from the black dot and the straight line below that. And then the center of mass or center of gravity is the place where those lines intersect. Their example here, they're sort of kind of looking at two ideas here, and that is that you can experimentally find the center of mass by suspending an object from 2 points and looking at the crisscross of those lines below the 2 points of suspension. And then also the idea that the center of gravity or center of mass doesn't have to be at the within the object, as in a donut, as in something that's the shape of the letter U or the shape of the letter L. The center of mass or center of gravity can exist outside of the object.